Okay. Hopefully it works. Janez, did you get any warning that this is being recorded?
Yes.
Yes. Okay. So hopefully it would work. So task parallelism as a universal concept, let's look at the approximate workshop outline. Why approximate? Because this is not a talk, this is a workshop, okay? I will try to make it interesting, and that's I would like to that's I would like you to ask questions in the meantime if you have any idea, whatever, and we'll talk about this. So this is approximate workshop outline. First, we will introduce parallelism of tasks in the real life. Okay, we will start with farmers working in the field. Okay, and then we will look at the motivation. Why do we talk about task parallelism? Because, you know, people who are not familiar with the computer, they don't understand that modern computers have many processors, many processing cores and things like that. They just think the big computer is a big computer. So small computer has small CPU, the big computer has a large CPU. This is not true. Okay, this was maybe true 40 years ago. Now it's not anymore. So this will be a bit of computing history, but again, we won't go into details. We'll just show what actually happened with the computers, that now we have to do supercomputing in a very, very different way that it was like 40 years ago. And then we will show how the supercomputer differs from a desktop computer. This is, again, without going into details, just show you why we need the concept that we call task parallelization. Yeah. After this, we will go through the real world examples. So more examples like farmers working on the field. We'll use examples from agriculture, transportation, industry, everything but the computing. Okay. Everything but the computing. And then we will also show the problems, okay? And we will try to see to show these problems in a way that is, again, not connected to the computers themselves. Yeah. So how does the, for example, deadlock look like in the real world? Yeah. Not in the computing. In the real world, what is a deadlock? They occur, they often occur, and maybe, you know, this workshop will actually enlighten you to see this concept in the real world, and maybe you will get some ideas how to organize even your projects as the things like this, because this is very general. And then we will talk about problem solving, parallelism in the real world. So we have actually the test, because this is a workshop. We have a test for you in the online classroom. I will show you how to log in, and you can actually try out your knowledge, what you actually receive, the knowledge that you will get during my talk. Again, your confirmation or your micro credit that you get for this workshop does not depend on the result of this test. This test is just for you to test out how good you are, okay? How many questions will you answer correctly and things like that. So it's not there to test you. Everybody who is here for the most of the workshop. Okay. So Payman, the problem is that you cannot talk if I understand, right? So if you see me, yeah, okay. So if you see me and you hear me, we are okay. Okay. If this is not the case, and I have to do something or try to solve something, we can talk about this too. Huh? Okay. So yeah, and then after that, we will go a bit deeper in something that is still not computing, but is a bit closer, tad closer. This is parallelism in mathematical problems, okay? Not computing, but going towards it. So no e-classroom, this will be purely interactive. We will look at two common problems in mathematics. And here I will ask you, I will challenge you, you know, how these things can be solved. Are there possible to be parallelized or not? Okay. And then any your questions you might have and so on. Yeah. I don't know how long this workshop will last. We just, to be on the safe side, we told you that it's about 19:45, so 7:45. I'm pretty sure we will finish earlier, but I would really like to have a discussion here. Yeah. So, first thing is task parallelism. Yeah, and you have to understand that parallel task is not parallel tasking, or parallel tasks to solve a problem. It's nothing new in the human society. Actually, this was before Industrial Revolution, the common thing to do. Okay, so here what we have here is an image of a farmer working alone in a large field. Yeah, so before Industrial Revolution, before we got big machines, so you have one combine harvester or a single tractor, who can just roar through the field and process everything, in a short time. You had people, peasants, working on their own small plots of land, or working for the owner of the land. Yeah. So what was then there? Of course, one single person could never actually manage that field that you see in the left. So basically, landowners who had big plots of land, how did they get them? It's another story. They actually needed a lot of not only servants but serfs. Yeah, people who actually worked in parallel. Yeah, and this was very common, as you know. All the big things in human history were actually done through the massive engagement of human work. So one of the things is pyramids. Yeah, this is one very, very known example of a massively parallel division of work. Now, what is the problem here? If you have massively parallel division of work, you have some people who do the same thing. Yeah. So you have people who chisel the stones, but not anybody could do this, because you also have people who move the stones, who oversee things, and so on. So basically, this division of labor is quite complicated. And it's the same problem in computers, but let's stay outside the computing world. So this massive parallel task is complex to organize, and very importantly, if you don't organize it well, you will be very inefficient. Yeah. So, for example, if you have single boss who supervises chiseling, then there will be a big problem if that single boss gets sick and nobody knows how to chisel. So not only the people who do this, but also the other people who help build the pyramid will have to idle, will have to be just without work. Yeah. And the work on the pyramid will go nowhere. Okay, so this is big problem. So it's not like if you go one screen back that you have like 10 people basically, I don't know, planting the seeds, and you get 10 times more efficiency that you have one person planting the seeds. Yeah, because you have 10, that directly translates to 10 times more seed being planted by the unit of time. But if you have complex things, complex task, then this may be very complex to organize. And the same it is in supercomputing, and that's why the high performance computing is, let's say, research and say the research area in itself. Okay, so now let's go to the computer history to see where the need for parallel task actually came from. So if you look at the computer, and this is a really basic task, we won't go into any programming and so on. Maybe you've seen this, maybe these things are sometimes even taught in schools in Slovenia. I know it's somewhere else. The computer is basically a device that processes data, and it had input devices, so where the data comes in. This is, for example, keyboard. This could be also the network connection when you download the stuff from the internet, and then could be output devices where the data come out, and you can browse it. So this is like computer display, or it can be printer and something like that. And then you have memory, okay, where the data is stored when it is being processed. So this is memory, yeah. And then you have secondary memory where the data is stored to be used later. And this is your hard drive, your SSD. So memory card, the places where the data is stored when it's not actually right now being processed, okay? And now the most important part of a computer is central processing unit. And central processing unit is the thing in the computer and the only thing, let's say generally speaking, that can do any kind of arithmetic, okay? So if you want to add 1 and 1, 1 plus 1, this is up to the computer processor, central processing unit to do it. There is no other, in the, let's say, general computer, there is no other unit that can do it as well. Now, in the modern computers, you say GPUs who can also do computation, but let's not go there right now. Okay. So now we have also here some register which store operands of calculation, control unit, but this is not very important for our task right now, because the problem now becomes, okay, how many computers do you have in the, how many processors do you have in single computer? And it becomes quite obvious, right, that if you have two processors in single computer, you can do twice as much computations. If you have 4, you can do 4 as much computations. And yes, this was one of the first ideas in how to actually improve the speed of the computing in the computers. And first, practical computers actually had very early the ability to, for example, do 2 operations in parallel. What does it mean doing it in parallel? You have one addition, let's say 3 plus 5 is 8, and the second one is like 4 plus 12 is 4 plus 12 is 16, yeah. And these calculations can be done in parallel because they do not depend on each other. So very early computers had this actual ability to do at least some computations in parallel. So, and the computation is the thing that we need computer for, okay, because that's why it's called computer. It's not called inputor or outputor, it's called computer. And so this arithmetic unit, arithmetic logic units, is the most important thing that we want. So we are actually interested in how to make it faster to do more computations. Now, what happened after that was not computers getting bigger, but computers getting smaller. And it come to the point where people could actually afford to buy the computer. So this, what you have here, this couldn't be bought. That's such a big computer like ENIAC. It was built by government, US government in this case, to calculate parameters of the nuclear bombs and simulate the explosions of nuclear bombs and things like that. Then later for the flight of intercontinental ballistic missiles and such really military things. Now, of course, in the minimization that happened later actually allowed people to bring the computer as home, and this is the situation that we are in now. Yeah, so home computers appeared like in 80s. Then, of course, for the offices, the special branch appeared like personal computers, like IBM PC, and what you probably have your desk. If it's not Mac, it's probably personal computer, which is roughly what IBM designed in the 80s. Now, what was important here that still here was one processor, then memory, output, input unit, and so on. And the question was why, how many processors were here, or let's say, why one processor? Well, the problem was that other things were not that expensive. Okay, you could put more memory in it. It was expensive, but getting two processing units in the computer, or let alone 4 or 6 or 8, was a big deal, because the computing the processor, so the central processing unit, was the most complex and expensive part. And for a long time there was no, except in a very high performance environments like supercomputing, you didn't have any of the parallelization that you would need it. Okay, so in 2000, things started to change. And why did it start to change? So let's look now at Gordon Moore and something that you probably heard as Moore's law. Okay, hopefully that you heard about it, and now we will actually explain what does this mean. And if you heard it, it would be nice if you say yes into the chat. Okay, so Gordon Moore was an engineer in before, not at Intel, but he was engineer at Fairchild Semiconductor, something like that. I'm not sure about that. And he actually said, well, the number of transistors, those are those small basic elements that make up the processor, will double every 2 years. Yeah. And then he said, after they asked him, after that, when he became famous, people asked him, basically, oh, you are very smart. I mean, how did they predict? And he said, oh, guys, I just did a wild extrapolation saying it's going to continue to double every year for the next 10 years. So he wasn't that, people read too much things into his Moore's law, that it's been called since then. But basically, what happened, so this is A is missing here, so it's Gordon Moore. Yeah, sorry, the E is missing. This law became very famous, and it mutated and slightly changed from every 2 years to 18 months, and it mutated from actually the number of the transistors were doubled to performance of the computers were double. He never said that. Yeah. So, and what did basically manufacturers do? So as we said, if you go back here, you have one computing unit, one processor in each computer. And what did they do to actually improve this speed at such breakneck speed? They just make processors faster, like meaning they make the clock at which processor unit ticks faster. So first personal computer in 1981 had like 4.77 megahertz clock. And then, if you go fast forward to 2005, we actually skip how much from megahertz to gigahertz. Actually, these things just insanely become 1,000 times faster. Okay, it really became 1,000 times faster. And then the word length increased. What does this mean? Very simply, your registers became bigger. Okay, all of this increased processor complexity, and then something happened after this, at this time roughly. So you can see this on the right side, that green line actually going through the years, yeah, starts far before the electronic computers with the Babbage analytical engine and the Hollerith tabulator, and then continuing and going first linearly and then exponentially. And basically people said, oh, it just cannot go like this. It will stop at some time. And they predicted, you see these red offshots, oh, it will level out now. It will level out now. It did not level out at the times what they predicted, but these things actually started to level up in the year 2005, maybe a bit before, of course, it started to level off as perceived by the people from like consumers, users on the computers. But of course, manufacturers of integrated circuits, of the processor and computer, they sensed it before. So it stopped growing, and actually it really started slowing down in 2010. So that's why, you see, in 2005 we have 2.5 gigahertz microprocessor, and now we don't have 30 gigahertz microprocessor, and there it's like, how we are now 18 years later. Yeah, so the clocks went nowhere. We just cannot push processors to tick faster. So there was a problem, and this problem demanded that for continually improving performance of computers, that some other ways found, even if your home computers, and then even in the phones, yeah, to do something else. And this else was, hey, let's put two processors in one computer. Not only one process, not only in the computer, but let's put 4 of them in your phone. Oh no, that's too slow. People are complaining. So let's put 8 of them. Okay, now we have a question. Why CPUs cannot run on a higher clock more than 5 gigahertz or so? It's a very good question. So, and what happens is, you have a motherboard, and typical motherboard in your computers is like this big. This is already big. A4 paper, maybe it's a little bit more, but it's something like this. Now, if you calculate like 5 gigahertz to the wavelength of the signal, you find out that you are at few centimeters. Okay, so what happens if you have electrical circuit that has the source of the signal here and the sink of the signal here, so the signal has to travel across the main board, you get the delay. So at such fast frequencies, basically you have here one value, and here it's still the other value, because at such high frequencies, even the speed of light with which the electricity travels is not enough to keep up with such huge speed. Okay, so this is the reason. Yeah, that's why we don't have 30 gigabytes or 100 gigahertz computers, because when you come to 100 gigahertz, then these distances get to millimeters. Yeah, and this is also, by the way, to explain to people who may be not familiar with that, why all the communications inside the computer, not all, but communications with the peripheral cards, with the disk, went to serial, not parallel anymore, because actually you came to the point where the data is transferred like they're literally flowing across the wires, like the bubbles would flow in the pipes. It would have actually transparent water pipes. So actually the speed of light has become too slow for those high computer clocks. Okay, so Jean, is this okay? Explains. Okay, if you have any questions, just ask it. Okay, so this thing started to go down, and people said, okay, let's cram more of the computers into more of the CPUs, more of the processor into one computer. And of course, the problem with putting two processors in it is it gets complex, So like in the modern computers, you have the main board, and then you put the computer in, the processor in with the heatsink and everything, and it takes up space. Put two of them, you're using up half of your motherboard. So what the Intel did, and they start actually producing multi-core computers, which means that you still have one processor, one computer integrated circuit, one chip, if you like, but they put two processors in it. Yeah, and we call these two cores, computing cores. They're the processors on their own, okay? And suddenly, if you do this, the computer performance doubles. And if you do it on the same die, like same, you can put 2, 8, 12, 24. Phew. Now we have here in our lab, we just got the supercomputing server, which has, I think, 2 processors, each of them having 64 cores. So in one integrated circuit, there are actually 64 processors. And now what are the implications of that? Can these things work faster? Yes, they can. But now we have a problem. As I will explain it to you, and then we will go to NVIDIA as well. What the people did, what people usually don't understand, if you want to have 2 processors in your computer busy, then you have to feed them calculations fast enough. And these calculations cannot depend on each other. So if we have a question or we have a problem that is, for example, let's say 2 plus 4 plus 10, those are 2 additions, yeah? 2 plus 4 plus 10. The result is 16, we know it. What do? You first add 2 plus 4, and then you add, okay, this is 6, you add 10, you get 16. Now, can we speed this calculation up if the computer has 2 processors? The answer is no. Why? Because the second part of the calculation actually depends on the first part. First, we have to know what the sum of 2 and 4 is before we can start adding 10. So if you have such a small, simple problem, very short calculation, then these parallel processors do not speed up anything, okay? And this is why then the problems arise. We will talk about them later. But now in the meantime, we go to NVIDIA. NVIDIA also did something in the years 2006, 2007. They call this thing unified shader model. Big word for a very simple thing. They totally redesigned their graphic cards. The graphic cards before were for gaming, yeah? Okay, shooting, gaming, 3D rendering, things like this. What they did, they found out that the architecture that they have is not going to get them anywhere, and they turned it upside down, and they designed their graphic cards not with special shader processors, which were there before, which were absolutely, those shader processors were actually specialized to map a texture, to get the influence on light on the texture and things like this. What NVIDIA did at the time, they actually turned it upside down, and their graphic cards from that point on contained many simplified but general processor cores. From that time on, NVIDIA's graphic cards could do calculation like 2 plus 6 is 8. And how many of these they put in, how many puts they pin? They started with like a huge number, like kaboom. They put in the NVIDIA GeForce 8800, they put 112 of those units. So this is like you have 112 units that can do addition or multiplication at the same time, okay? And suddenly these things become useful not only for graphics, but for general purpose computing. And as I said before, you know, in the modern computers, your graphic card can do mathematical calculations as well. So this was the other thing happened at approximately the same time, because they were thinking about, well, you know, the Moore's law is dead, you know, people would want to have different kinds of solutions. And now, beyond 2007, things went into this way, increasing the number of cores, which became this standard way to cheat Moore's law. And maybe you heard, I didn't know how much did you listen to these things, but then, oh, here it is, new phone, it has quad core processor, because the old one is too fast, it had only double core processor, sorry. Then 8-core phone. Oh, this is even faster. Snapdragon, I don't know, 8-core processor, things like that. So they just started to cram more and more into single processor, more and more cores, and the result was that you had more and more CPUs even in one simple phone, not in, let alone your desktop or laptop computer. So why? As we said before, it's no longer possible to overclock processors to raise the clock to very high frequencies, and these serious problems which begin to occur, this is what I explained before, you know, actually speed of light becomes too slow for us. And basically Moore's law just has been severely challenged, and that's why problems start to appear. And now we have to deal with a lot of processing cores for any processing task that we need to do faster. Okay. And so where we are in 2023, we have at least 2 cores, preferably 4 or more cores. You will be challenged to find the computer or even laptop with only 2 cores, new one, I mean. And you know, the things can become insanely inexpensive. You know, you can get a processor from the data center that has 12 cores for $100 and graphic cards. So still the thing that you use to shoot aliens, yeah, still these things are used for computer games, but they are general purpose computers which can have 500 cores to 1,000 cores, and you can buy it for 200 euros. Yeah, and if you just slash out and you splash out, sorry, splash out and pay $2,000 for your graphic card, you will have many cores. They go into thousands. So you have 1,000 parallel units that can calculate how much 1 plus 3 is. Okay. So, as we said before, even if you have 2 cores, then you cannot just speed up your computer by that, because before of that, when the this increase of clock speed was not a problematic, you could just run your processor at twice the speed. Maybe you cooled it down. Yeah, maybe it didn't work, but the new one did work, and it was exactly twice this. It was exactly twice as fast as your calculations. If you put 2 cores, this means 2 processors in parallel. This is not true. They're still working at the same speed, but you have more of them. And this is what the old landowners or landowners in the history a long time ago had. You know, they didn't get peasants or serfs that work very hard. Yeah, they just get more of them. They work at their same speed, and if you want to have more, you just hire more, you know, or just conquer lands and, you know, enslave more, whatever they did in the history. So, and these things came to of course, to the attention of software developers, and now even the modern software that you run on your computer tries to take advantage of this. So now, for example, in 2023, if you have a browser, multiple tabs, each of the browser tabs runs into as its own task, and in theory, it can work on the different processor. Yeah, so that's why your new computer still means still runs snappier, faster, because people start to adapt the software to the parallel processors, yeah, to the high degree of parallelism, which is not a trivial task, as you will see in the next 2 hours. So now, what is a supercomputer? Okay, now a reminder again, if you want me to explain something, you didn't understand something very well, just ask me in the chat. Okay, so now we have the question, what is a supercomputer? Now, long time ago, you know, these are big devices, and like we saw here, you know, this is like a supercomputer, and you can see it. Oh yeah, it's supercomputer. It's in the room that's obviously very loud and cold because of the air conditioning, and there is a lot of cables probably and things like that. But and let's say 40 years ago, you would say, oh, supercomputer has a very fast processor. But now, basically, the difference between your computer on your desk, bought for like 500 euros, or Raspberry Pi, who costs like 50 euros, and the supercomputers is simply that the supercomputer has a lot of processor units, okay? So your computer has at home maybe has 4, 8. If you have a modern computer and like to play a lot of games, it may have 12 processor cores. Now supercomputers have thousands of processor cores, and if they have NVIDIA graphic cards or some other graphic accelerator, then may have 10,000 or hundreds of thousands of those simplified basic processor cores from the graphic cards. So if we look at Slovenian supercomputer in Arnes, yeah, it literally has 4,200 of Intel, I think, or AMD, I don't know, but PC processor cores. So this is still, at its core, this is still the same kind of computer as you have it on your desk, just it is multiplied many times over. How do we make it faster very quickly? Well, we add another 4,200 computing cores, up to some point where the problems start to appear. Also, you know, this supercomputer has 18 terabytes of memory. You know how much memory your computer has? It's probably something around 8 gigabytes, 12 gigabytes, 16 gigabytes, 32 if you have really, let's say, heavy loads to run, then it's like maybe 64 cores, something like that. 64 megabytes. But Arnes supercomputer has 18 terabytes. That means 18,000 gigabytes of memory. Now, how does this physically look like? Well, these are not 1 terabyte models, you know, that you put in this computer. No, because this computer is as effective as an architecture composed of a lot, maybe 200, 300 motherboards, each with, let's say, 4 processors and 2 GPU units, yeah, and then just this together in the same room makes it a supercomputer, yeah. It just many times over multiplied ordinary computer. And of course, these units are connected with high speed link. So that's why we call it supercomputer, because it's as a one unit. Okay. So first thing that we have to really say that it's not true here is supercomputer is not a very fast computer with very fast processor. If this would be the case, we wouldn't have this workshop, yeah? Because then you would just use it as or any kind of ordinary computer, just everything would run very fast. Technology does not allow us to use, I don't know, terahertz frequencies. No, we are still stuck 3-4 gigahertz. And basically, it's just a computer that has a lot of ordinary processors. Now, to make use of the supercomputer, we actually have to prepare the tasks in a way like the old landowners in the old times needed to do, or the Egyptians when they did pyramids. We need to make sure that whatever task we have is actually split into many subtasks to keep everyone busy. You know, every working on a farm or in the field, every guy there building up a pyramid, or in case of computer, every processing unit's crunching numbers. Yeah. So, and this is the problem of task parallelization. Any questions up to now? Okay. Sometimes you will hear that processors have virtual cores or hyper-threading, and these are marketed like, for example, you have a processor that is sold like, oh, this has 8 physical cores but 16 hyper-threaded cores. This is just a very, let's say, a very big marketing trick. It goes like this. When Intel was proficient in building multi-core processors, so with many CPUs, it found out that even if we run the programs that are not parallelized, that part of certain processor was not totally used, okay? And let's go back here and I will show you, whoops, okay. For example, let's here even back. Okay, so you see the central processor unit is built off of many components. Those are just 3 main ones. And every core in the computer processor is built like that. Each processor is like that. So it has registers, it has arithmetic logical unit, it's its control unit, prefetch unit. You know, there are a lot of different parts of the processor to make it work. Now, and Intel find out, let's go on, to what we had now, Intel found out that some of these parts inside of processor are not very well used, you know. So even if you run it at high, even if you totally overload it, or let's say totally load it, your processor with some computational task, some parts of the processor core were not used. And then they said, okay, so let's make it visible to the computer, or let's make it visible in a way as we would have additional core. So when multi-core, sorry, when modern processor presents to the computer, to the operating system, to the software, what happens? Usually, what your software sees is, for example, 8 cores, but inside the integrated circuit, inside the chip, there are just 4 of them. You always see double. Why? Because the processor then actually advertises that it's more powerful than actually is, and this additional core, which is then like 2, as a colleague said here, have 2 threads per core, something like this. This means that Intel has 1 core that actually works, but if that core has some spare capacity, then another task can run on this same core, but is visible as separate core. Okay, so in practice, this means that you can look at your computer that has like 8 physical computing cores and let's say 16 virtual cores or hyper-threading core as being like 30% faster than the one that has let's say just 8 cores and no hyper-threading. Okay, so this is the difference. The other tasks may run at the same time, but just both of the tasks, that's why it runs slowly because of that. Because, for example, if you have arithmetic logical unit that is not used in one task because it waits for data, then the other process can do some computation on it inside of the core. Okay, and then when the other process actually gets its data, then this arithmetic logical unit will process data from the first processor. So they share things, because very few, this comes from actually from the inefficiency in the program code, because the code as it runs does not need all the parts of the processor at same time. So basically both tasks, when running on the same cores, like 2 virtual cores, slow down a bit, but overall, you can do 30% more computation. Okay? So, Jean, this explains it. Yeah. Okay. So if you didn't understand this last part, don't be afraid. It's nothing critical for the super computing. Usually when we talk about supercomputing and power, so we talk about physical cores, actual CPUs. We don't ask ourselves how many virtual cores and things the processor has, because the real computation actually with like two cores doing twice the amount of work happens only with physical processor, physical cores. Yeah, the rest is marketing. Okay, any other questions here? Okay, if not, let's continue on task parallelization strategies. So why we need this task parallelization strategies? Because, you know, we have in front of us the computer that is supercomputer, it's parallel computer. It can solve a problem very fast, just like thousands of serfs can plant very large fields, but it's of no use to us if we don't give those serfs working for us, yeah, if we don't give them, let's say, the tools to do it. If only one of those, let's say, serfs or farmers carries the seeds for planting the seeds, yeah, then only he will do any work. The rest of them will just waiting. And it's the same problem that we have here in supercomputers, or in general in very fast computers. Nowadays, modern computers who have more than one core, like if you have 8 cores in your computer and you don't care about this, what I'll be speaking now, then you're effectively using just 1/8 of your available computing power. When does this become important? Well, when there is some deadline in 1 week that you have to meet, and you find out that your work will be done in 3 weeks, not in 1 week. Yeah. And then it pays off to use the full power of your computer and do your work like up to 8 times faster. And now we will look at the ways how to split our task into multiple, so our big task, our computing problems, into small tasks. And again, we will go back. Now we are going far away from the computers. I hope I didn't scare you with explaining of the processor. And so we're going back to the world outside of computing. Yeah. So one of the things that is very simple are these serfs or even machines in the field. So first concept that allows you, and it's actually the simplest one, to solve your problem in parallel, yeah, if you have a task that requires processing a large amount of data. And this data is independent of each other. Okay? So you have a large amount of data and you process it with some operation that can do it on each piece of data together. What would that be? For example, like in computer world, it would like you have 1,000 of images and you have to do something with those images. Maybe you have to convert them to grayscale, or you need to, for example, find out who is on those images. Let's say you have face recognition, you want to do it with computer, and you have 1,000 images. What you can do, you can run it and as a task, sorry, as a one image after the another, and we call this in a sequential way. Yeah, or the one processor, you process the first image, done. You process the second image, done. Now, because images are independent of each other and this task is independent of each other, what you could do is use 64 processors and like let them do this in parallel, process 64 images in parallel, and then next 64 in parallel, and so on. So in general, we do this a lot of times in the real world. And one example is agriculture. Okay, so what we can do first, we have one, for example, what is done in the big farms. You know, what big farms are afraid of? Unfavorable weather condition that will destroy their crops. So at some point, you know, the crop is ready to be harvested, and they need to be harvested right now and not like take 2 months, because by 2 months the crop will rot. What they can do? Well, they don't have one combined harvester. If they're really big, they have multiple combined harvester, and they can do it in parallel. And this is actually a concept that is called data parallelism. And here the crop, yeah, the wheat or whatever, is actually the thing that you split to multiple small pieces. So let's say the area of the crop, the area of the field. So one harvester works in one part of the field, the other harvester works in the other part of the field, and the third one works in the third part of the field. More harvester you have, the faster you will be done. Okay, so this is data parallelism in our agriculture. Now, if we go to cooking, okay, you can see this also. So you know that if multiple guests order the same dish at the table, the waiter will be happy and cook will be happy as well. Why? Because he can prepare these dishes in parallel in an easy way. Otherwise, he has to do it in parallel, but this is in an easy way. So if you have several portions of the same thing, you can do it very efficiently. Now, if we go from the high class cooking to, let's say, your mess at university, you know, where there are just 2 or 3 menus, yeah, how is this parallelism done? Yeah, if like you have 100 people that will eat the same dish, what do? You just take a large pot and cook everything in the large pot, not in the small pan. Yeah, so this is actually the concept of the data parallelism in cooking. Yeah, in parallel you do multiple meals, and all of them are the same. This is very important. Like the crops here are all the same, and they do not depend on each other. Okay, now tourism. How does this work? You may have, you know, imagine this, how would be very, very wrong way to actually for the tourists to see some kind of exhibition, like you have here the Pisa Tower. Yeah. So what do you have? You have one group of tourists with one guy. You have other group of tourists with the other guy, and they're all looking at the same thing. Yeah. So why they're looking at exactly the same things? They can do it because you have multiple processors, and those processors are your tour guides. Yeah. So if you have like archaeological place, or you have some other kind of ruins, or some things that are not yet ruins, like this Torp in Pisa, sorry, you can actually have multiple tourist guides, and these multiple tourist guides can actually have people explain to people, and at the same time, like instead of 10 people, there is 100 people looking at the same thing. So this is again data parallelism. Again, these people are doing all the same thing. All the groups are doing the same thing at the same time. If this thing allows it, like if you have Tower of Pisa, that can be 10 groups instead of one group looking at the tower from outside. Yeah, no problem. Any kind of other ruins. And then very, very often found solution to the problem when you have a lot of the same product. You have industrial production with a very high throughput. Yeah. So for example, you have the same operation. Yeah, we said this, like assembly, packaging. It's done on the different instances of the same product at the same time. So there is like 100 apples coming through your production line in each second, and all of them are being packed. Why? Because you have like 100 people packing them, or 100 machines that all pack apples. Yeah. So, and if your work is too slow, you can just buy 100 of the other machines, and now you have 200 machines packing these things. Again, the concept of data parallelism is that these objects entering the processing, like pieces of data, do not depend on each other. Okay, this is very important. And then you can do this. And this is also the most trivial way for any of you who want to do do, let's say, parallelization on the chip. Yeah. And let me say how you can do it. Okay. So, like, practical example, not in theoretical or programming point of view, but let's say you have a deadline for the conference. Yeah. And you have 2, let's say, research papers that you need to send out. Your boss said you have 2 research papers. And of course, for each of them, you need some computing task to be run. What do? Yeah. You take 2 computers. Okay. You take 2 computers and you run maybe the same thing, same calculation. Okay. So, okay, not the two papers. Sorry, I made a mistake. I skipped here. Task parallelism, but data parallelism, what you can say, okay, you need to process, I don't know, said 100,000 images of something, and then you ask your friend or just your co-worker to lend you his computer, and you do 50,000 images of one and 50,000 images of the second one. And this is usually the least complicated and, let's say, the best kind of use of parallel resources you can think of if your problem can be split this way. Often, the problems cannot be split this way because you have different tasks. You don't have the same task, you have different tasks. Like here we said, all the apples are being packaged, okay? So all the apples, you have same things. So here we said, all the people are looking at the same object. Here we said, the cook is doing all the same dishes, and this makes him very, very, that makes him be able to do it very, very optimally, because, you know, once he takes the I don't know, the splash of spice, he just grabs it 8 times, it just poof, puts it over like 8 pans of the same food. If those things are different, he cannot put the same spice over 8 of them, because these are different dishes. So now we go to another concept, a different concept, which is task parallelism. So what is task parallelism? This is the situation where your tasks are different, but you are able to do it at the same time. And one nice example for this is many transport operations, like airport. Okay, so in the airport, you know, imagine what would happen if you wouldn't have this highly parallel system. You come to the airport, you have your luggage, and there is a person. You put your luggage there, you know, checks it in, and then puts it as a conveyor belt. And then this same person goes on and fiddles with your luggage, puts it on the trolley, so it goes on to be loaded on the plane, and later it goes and loads it on the plane. And that same person goes on with you, and you have, for example, boarding, yeah, and the same person looks at your boarding ticket, and then at the same time, this person lets you in the plane, and then it goes up at the control tower, and it's again the same person saying, okay, you have you have permission to fly. This would be very, very inefficient. So what happens in the airport is task parallelism. Different tasks done by different, let's say, processing units, which are people, yeah, doing various different tasks in parallel. So somebody is checking in people on the check-in counter. Somebody else is handling the luggage. At the same time, the other airplanes is departing, and somebody else again in the tower is actually synchronizing them, giving them permission to take off or to land. And there are gate agents who actually check your boarding passes and let you at the phone. All is this going at the same time, because this is simply efficient way to do it. What do you need? You need a lot of people. You don't need one people. You need a lot of people, but these people need to be let's say trained in different tasks. Yeah, you cannot just put baggage handler on a check-in, let alone in the control tower. Okay, so this is called task parallelism, because you have different tasks working on the data. It could be the same data, it could be different data, but this is task parallelism. Now, another such example is construction. And, this is how I started with pyramids of Giza. Yeah. Some guys were chiseling. Some guys were pushing those large blocks. Yeah. Some guys were pulling the ropes. There was some guy who was measuring, is this everything aligned? Yeah, there are many of them, probably not just one. Yeah, they're also working parallel to see that everything is straight up. So in construction, it's the same. Yeah, you have several workers doing different jobs at the same time. So one worker is mixing concrete, the other one is laying bricks, the third one is carrying out electrical work. Is possible. Not all things are possible. You see, now we are coming to the problems. Not things are possible at the same time. Yeah. So construction, this is task parallelism. Entertainment, yeah, big music festival with multiple stages. You have, again, people wanting to enjoy themselves, but they have different tastes. And of course, very useless would be like you have one stage and then somebody's performed there. And then you have the other band performing there, and then you have the other band performing them. Because if this is a diverse crowd, they don't actually need to listen. They won't want to listen to everything, and you can split it up. If it's a big part, you have alternative bands at one stage, you have home bands at the other stage, you have mainstream popular bands at the third stage, and everybody chooses where to go, and you can run it in parallel. Yeah, so the people are happy, so they're not protesting, oh, what, you good enough for 2 hours when this band I don't like is playing there. Okay, so this is task parallelism. Why? Because there is actually different activities going on. Yeah, not the same activity. It's not like you will have 3 bands playing the same song, yeah, everywhere, because this would be ridiculous. You don't need this. Yeah. So we came through 2 of the concepts. One of them is task parallelism. The one before was data parallelism. What is the difference? In data parallelism, you have the same task done on large amounts of input data, or let's say product, if it's this in real life. In task parallelism, you have different tasks that you do. Which one of them, what do you think, is more difficult to organize? Data parallelism or task parallelism? Now, I'll wait. I want your answers in the chat. Which one is more difficult, task parallelism or data parallelism? Well, I'm waiting. Okay, Jean said task. Okay. So, Jean, you said that is task parallelism is, yeah, okay. Yeah, we're getting there. So you listen, hopefully. Okay. Why? Because they're different tasks and they all have to go somehow in unison. Yeah. And you see here, you cannot install electrical wires before actually building is built. Yeah. So it's much more difficult to organize. So that problem, like we say here at agriculture, you know, you just put 10 harvester on the field. You know, even even if you have many harvester, but since they do the same thing, you just it can be just one. They can be just literally just in parallel going through the field, do it in 1 minute, everything is done. It's trivial to organize. Now in task parallelism, yeah, as you know, running airport is a complex thing. Running construction site is a complex thing, yeah, because some things cannot come before the other, so you have to synchronize that. Running music festival is a complex thing, yeah. And now we go even further with this concept of task parallelism, and we look at the pipeline parallelism. Now, what is pipeline parallelism? Pipeline parallelism means that we have different tasks, but processing the same data in particular order. Now, somebody will say, yeah, but this is true for the airport. It is partly. You cannot board airplane before you get checked in. But there are many things that go in truly in parallel and they're independent of this. So, for example, in the airplane, on the airport, boarding is totally decoupled from loading your luggage on the plane. We know that because we lost our luggage sometimes, yeah? We know that this thing is decoupled. They don't wait for you, and your luggage may be on the plane, and sometimes they don't wait for your luggage to come, and you are on the plane and you fly away, and then you find out the destination, your luggage didn't come with you. Yeah. Now this is like task parallelism in the airport. So things are not necessary, these tasks are not necessarily in the particular order. But in pipeline parallelism, they are in the particular order, which somehow changes the things, makes them better organized. So for example, here it is again in agriculture, we have baling. So the baling is the process of gathering hay into bales, wrapping the bales and putting them down. These are carried simultaneously, but all steps are interconnected. So if you have this baler, what this does, it scraps the dry grass, yeah, the hay, and then it's pushing it in, and then it's already rolling the stuff. It never stops. Okay, so this is very short pipeline. Important is that these tasks, like squeezing, like grabbing the hay, squeezing the hay, and wrapping the hay, are done in the particular order. Yeah. So this balers usually, yeah, as those can be big long machines, you know, they at the same times they're grabbing it, at the same times they're pushing it together, and the same times they're wrapping it, you know. So this is pipeline. Why pipeline? Is a pipe, yeah, line in a pipe. Things go through a pipe in order. Very good example of what we call in the computer science pipeline parallelism is actual modern production line. Let's say the process that was invented by Henry Ford. Okay, so how were the cars produced before the Henry Ford? You had the team of mechanics. That team of mechanics first put together the chassis, yeah, the wheels. Then they just took the engine, put it on, yeah, and they just screw the engine on. They put the cabin on and think. So like the same, let's say 2 to 4 mechanics. Maybe you had 8, but they made the car to the end and they finished it. You know that this was inefficient, right? Everybody learned about this innovation that was, let's say, modern production line. What did Ford do? It's actually he split the individual operations into very small parts that actually run in a pipeline. Why? Because it's very critical for the car quality that they're done in the exact order. So first, two guys put the chassis together, then two guys put engine on, then two guys screw it on, and this can be very small parts of work if you've seen the modern production line. Yeah, you can literally have things is going slowly and the guy jumps with the wrench just and then moves away. Another comes. So as those cars moved to the production line, basically they move to the production line, they are getting more and more processed, which means completed. Yeah. And now the question, tell me about this, why is as I described here, why is that modern production line more efficient than combining all tasks into one big, let's say, one big construction, like 4 people construct the same car? Why do you think? Why is that more efficient? Now you can put your ideas in the chat. Now, if you want, you can also, you'll be recorded then, but you can if you don't mind, you can switch on your microphone and tell me. Yeah. So why is the modern production line more efficient? Oh, very good, Janez Križaj. Yeah. In each step, workers are focused only on one repeating task. So you hire a new guy because which needs to fill the position in, I don't know, wrench screwing department, yeah, on the production line. Like you have like 200, I don't know. I'm not sure how many they have. Like they have 200 positions. One of them is screwing in, you know, one thread. So what do you need to teach that guy? Only that part of the process, just this, yeah, and you can train him very quickly. So how does this go to the, how does this relate to the computers? Sometimes you have processing units which are very specialized, and this was actually something that was done in graphical cards before NVIDIA introduced its, like unified shader model. Yeah, actual processors. Before NVIDIA introduced the new processors, actually graphic cards had a processing pipeline. What was the processing pipeline made of? First map the texture, yeah, then apply the lighting, and then do post-processing. Okay, at least those 3 steps, and they're in pipeline. Yeah, so Pixel just went through the pipeline. And why was this good? Because the part that applies the texture need to do just applying texture, and this was very simple, let's say simple piece of integrated circuit which could do this at the amazingly high rate. Okay, so like the guy who can basically, what he does, it only needs to screw something in, he can do this very quickly. Yeah, if that guy needs to do like 200 different tasks to complete one car, then he won't be very fast at each of those tasks. So pipeline parallelism is actually the way how you use specialized computing stations, let's say. Yeah, you just push the data through. You know that all that data pieces have to do some order of operations, and you do it through the pipeline. Cooking, yeah, for example, again the pipeline. So, for example, if there is a really big demand for food in the fast food restaurants, they have many people there. What they do, one cuts the bread, the other one it's frying, it's turning the burgers, yeah. The third one adds sauces, yeah. And if you want to see this in practice, go to Five Guys restaurant where they literally work this way. Five Guys is an international, mostly American hamburger chain where they have a long table, and then first person does something with the burger, passes it to another one. You have to go there when they're really busy, okay? And you can watch them from behind the counters. So they show, actually they're showing off how they're doing it, and you'll see this pipeline. Again, specialized workstation. That guy only puts sauce, the other guy only puts patties on, and so on. They don't have like 20 workstations. They have about 3 or 4, and all the burgers go through it. Yeah. So why is this important? You have specialized stuff. You have the low training to do the stuff. Now, when there is not a lot of people, yeah, you need one person who knows to do everything, to make burger from beginning to the end. But when you have a lot of people, you have to do it very quickly. It pays off to have specialized things. Like in the computing, before NVIDIA came with the unified shader architecture, literally every graphic card has 3 or 4 specialized components because they are easier to manufacture, just like people are easier to teach just to flip burgers than to do everything from the beginning for a burger. Now, these are 3 concepts how we can actually parallelize your work. Now, hopefully, you're people who are interested in this because your work somewhere, either in research, in this industry, academia, or everything, has a problem that could be solved on a very powerful computer, and you're interested in the fact how to do it quickly, how to do it efficiently. Yeah. And up till now, it was all fun. Yeah. And no problems. But now what it happens is, it's not that easy. You have some problems, and these problems can actually, if you don't handle them correctly, stop everything, And now we will look at the problems of task parallelism, okay? So if it would be like easy, as I said, then, again, we wouldn't need this lecture. So let's go to see what are the problems. Some tasks cannot be divided into smaller tasks that would run in parallel. In this case, actual parallelization, like splitting tasks, is not possible. We cannot use more than one processing unit. I don't know what your position is where you work, but sometimes if your boss where you work is fair, then usually he takes a lot of work that cannot be split among you. Yeah. So there is one person who needs to handle the money. Yeah. Needs to coordinate the teaching, for example, and things like that. So it's very difficult to speed up those. So we have some things that we can call inherently sequential tasks, and those are mean things. Yeah, those can actually destroy our all nice ideas to using parallel computer to do the things faster, multiple cores to do things faster, or even prevent us from doing a supercomputer. And now we'll look at the example again from the real world, what inherently sequential tasks are. Okay, so let's go. In agriculture, yeah, caring for animals or plants is an inherently sequential task that cannot be parallelized. Okay, it needs constant care, observation, and this care has to be done in specified intervals. Okay, you cannot take, so for example, you have cows, yeah, and if you have like 20 cows, it does not pay off to have 20 people feeding the cows, right? Because one person will take the wheelbarrow with the food and throw some amount of food to the cows, and it will done this in a very quick time, and then yeah, it will take do some other care of them, and then he will milk them, yeah, with the machine or without, whatever. And these things cannot be just parallelized, they are sequential. Yeah, you cannot put 5 people on milking one cow, because this would be like totally inefficient. This doesn't pay off. So, and you know, the cows need to eat multiple times a day, probably not once. You cannot just throw them huge amount of food, yeah, or let's say you cannot throw them 1 week worth of food, and you cannot just milk them once a week. You have to do it every day. So these things, this thing is inherently sequential. You feed them first day, you feed them second day, you feed them third day, yeah, and then after you feed them each day, you milk them, and so on. Okay. Entertainment. In entertainment, there is like creation of the work of art. Yeah. You cannot just take 10 artists. Okay, this would be very nice modern art project. Okay, but we're not about that. 10 artists with 10 brushes painting the thing faster. Okay, because it's not about making realistic painting. The modern art is about the artist basically looking at the picture, improving it, looking at the model or the landscape, whatever, and then improving. It's iterative process. Okay, modern art, it's iterative process. Okay, so until someone is satisfied with this art, 10 painters, if you want one image, this does not work. Okay. Healthcare. This is one of the most the most important concepts here. Yeah. So the diagnostic process is often inherently sequential. It can be parallel to some way, but if you come to the doctor and said, I have pain in my stomach, he won't immediately order CAT scan, MR, I don't know, blood tests, everything. When you have, maybe if you have very, very, let's say, high Mercedes kind of insurance, he might do that. But even these things cannot be done in parallel. So he wouldn't order a ton of tests at the same time, and then the surgeon who will just open you up because he has time and now and look at you and says, oh, it's nothing wrong with the guy. So healthcare and medical diagnosis is often iterative thing, you know, and you cannot do actual next step before one step is finished. First the blood work, and then we can see, we send this guy for operation, urgent. We will give this guy a pill, yeah, something that could be cured by taking medicine, or we order further tests, and now we know that we won't put him to the CAT scan, but we'll put him to the MR, because what we've seen from the blood test is to speculate about something. So this, hopefully, it's very obvious why the medical diagnosis is inherently sequential tasks. Okay, because these things cannot be rushed. So, and if you have, like, you know, imagine, you know, this is now very crazy scenario because the doctors are in short supply everywhere. Okay, but imagine that you come to the medical practice, you said, oh, it's my stomach hurting, and then 10 doctors start working you. It's impossible, cannot be done, wouldn't make things any faster. Yeah, you will just waste their time and your money if you're paying 10 of them at the same time. So Until this part, things have been still straightforward, and hopefully you from each your own fields that you're listening here to me can imagine things that actually that were actually in your field of work that are actually inherently sequential. I imagine that they are, you know, at least your daily routine is you have to work and rest and sleep and work and rest and sleep. You cannot just work for 5 days in a row and then sleep for 5 days in a row. This is impossible. It does not work. Yeah. So hopefully you can imagine things. I want to ask you about this, but I'm asking you to think about it. What are the things that you can actually do? Okay. What is the difference between pipeline parallelism and sequential task? Very good. Very good. So these were the question. What is then the difference between pipeline parallelism and sequential tasks? If you have pipeline, you still are able to find things that can be done optimally in parallel. And if we were talking about doctor's office, okay, here, you can solve part of this problem if you have multiple patients, okay? So what do? Basically, the well-oiled health system works like a pipeline, okay? So the doctor looks at you, orders blood tests, and sees what is the reasonable cause of your problems, and then it refers you to specialists, yeah, or some other test. And then while you are the specialist, he's already talking to another patient, okay? So if you have inherently sequential tasks, but you have a lot of data to process, you can construct a pipeline, okay? But if you have one task that is one person who is ill, and you know, then you cannot do a pipeline because there will be just single bubble going through the pipeline, yeah, not many of them. So yes, what you did is what you ask is very good question. Basically, if we have inherently sequential tasks, but we have many of these tasks, we can group sequential tasks into a parallel, but we cannot split those inherently sequential tasks, okay? So Payman, is this the answer that you looked for? So we cannot split inherently sequential tasks, but we can group them, yeah? If we have more tasks. Now, if it's just one person who is ill, then we cannot do anything. You cannot speed it up. Okay, any other questions? Okay, so if not, we will go to one important thing in parallel computing, which is Amdahl's law. Okay, and this is very often explained, but most of the people don't get it, because now I hope it will be very clear to you, because you listened to me for the past what should I say, 2 hours, 1.5 hours, and now we will somehow come to that conclusion why parallelization is different. Most of the tasks that you deal with in your life or in your professional life, and in the end, if you're with your work with computers, are mixed tasks. For example, and this Payman got a very good example as, for example, healthcare. It can be partly parallelized by using the pipeline, but inside that pipeline, you know, you cannot split things further, yeah? So often we have parts of our processing that can be done in parallel, but other parts cannot be done in parallel. And this is now the problem. How efficient are we? Is it even worthwhile to parallelize a task? Okay, should we get another doctor in the, let's say, I don't know, hospital or not, or we just that doctor, due to the nature of the task we do, just look in the air. Yeah, we don't want to employ them. And this is also goes for the computers. Well, should we buy more multi-core computer or computer with 32 cores if our task at hand is mostly sequential? Then our things won't work very well. We won't use this. And now we will again go through the real world examples of mixed task. Okay? So moving hay, yeah, is a task that can be partially parallelized, as we said, like harvesting. Okay? So mowing hay, it can be parallelized just like harvesting grains. But after you mow the hay, yeah, and you get what is this? You know, you mow the grass, it's still wet, falls down, then you cannot do anything, but you have to wait for it to dry. So that first part can be done very quickly. And now comes the key understanding of Amdahl's law, okay? And I will explain it here, okay? So you have one tractor who can mow your enormous field of grass in 7 days, okay? And the hay needs 1 day to dry so you can put it away. Now, is it worth buying another tractor? Oh, I'm waiting for you. So the hay dries in 1 day, and your tractor needs 7 days to cut the hay on all your fields. Now your answers. Is it good if you buy another tractor? Will it increase the processing of our hay? Okay, Jean said yes. Okay, why? Because if we buy 2 tractors, and let's say they're 7 days, we can actually cut the grass in 3.5 days. Will the hay have enough time to actually dry? Yes, because it needs only 1 day. In fact, we can buy as much as 6 new tractors to have 7 in total, yeah? Because if we have 7 tractors, they will all be able to cut the grass in 1 day, and then basically the hay will dry for another day. So instead of using 8 days, so 7 days for cutting the grass and 1 additional day, so the last part of the cut grass dries into hay, we can actually speed it up in a way that we have 7 tractors. First day they cut the grass, they do it in 1 day because there are 7 of them, and then all this grass dries in the second day. So now we use 2 days. But now something important happens. How much speed up did we get with this? We multiplied the number of tractors by 7, okay? And what was our speed up? How fast do we do it now? Answers in the chat, please. How much faster is now our processing of hay? Well, before we need 8 days, now we need 2 days. How fast are we? I'm not going on until somebody says something. Yeah, it's very trivial. There is no hidden problem here? Okay, Jean, may I ask you? No, not infinitely faster. 4 times faster because, okay, 3 times. Before we need 8 days, now we need 2 days. It's 4 days, okay? Because before we needed 7 days to cut all the grass, 1 day for the last grass to dry, yeah? And so there were 8 days in total. Now we cut the grass in 1 day, and this all grass is drying. Of course, it's drying in parallel in another day. So now we are done in 2 days. It's 4 times. But here is the catch. Oh, it doesn't matter if it's 3 times or 4 times. Okay, so Arslan, it's okay too. But the problem is we invested 7 times more of tractor to speed up our process only 4 times. You see, and this is the basics of Amdahl's law. What now happens if, for example, we invest not in 7 tractors, but 14 of them? So then they will cut the grass in half a day, yeah? And the grass will need 1 day to dry. So now with 14 tractors, we cut it. So with 14 tractors, we reduce the time to 1 day and a half, okay? Now, if we have 100 tractors, we still will have hundredths of a day plus 1 day for drying. Because you see, part of our process, part of our task of putting away the hay is actually sequential. The hay will dry for 1 day and no way around it. We cannot get it under 1 day, okay? And this is the core concept of Amdahl's law. There is the limit. How much parallelization can we do to even speed up the things? Okay, so I will look at I'll show you another example. Cooking, yeah, this is another good example. You can in a restaurant, multiple chefs can prepare various tasks, various parts of the menu, but the dishes need to be served in a specific order. Okay, so we cannot just we cannot just cook 7-course dinner in 1 hour with 7 chefs, because people eat food sequentially. Okay, we cannot just dump everything from the entree to the dessert on the table in the same day, because the part of the dining experience, part of the dining is sequential. People would like to eat like in a big banquet dinner. They would like to eat it in by sequence and chat between it. So no, if you have like one guest, yeah, or let's say that you have 1 cook that can do 5 things in parallel, you can do five guests at the time, but you cannot just add 7 cooks to make it even faster. It won't work. They will have nothing to do. You know, you have 5 guests, one cook may perhaps cook like 5 dishes per hour. In 7 hours, you know, he done 35 dishes. Guests can come from entree to the dessert, but you cannot speed it up. Simply you can't. Okay, so this is again example of Amdahl's law. Now you see I have here only 2 examples because I think this is enough. Okay, because it's getting, once you get this good impression of what are sequential tasks, what are parallel tasks, you know, it gets very easy to see the problem of somebody actually try to employ 7 chefs to get the dinner through faster. You can't. Yeah. Now we go now to another problem, which is called pipeline stall. Okay, and pipeline stall is problem when we have tasks running parallel if they are interdependent, if they depend on each other, okay? And this is often the problem in pipelines, because we do pipelines, as I explained before, to payment. We do pipelines sometimes, like in healthcare. Yeah, you have here the patient. Patient comes, you look at him, do some tests, then move it to the other doctor, the specialist. The specialist then moves it to surgeon, and so on. But if the tasks are dependent, then we have the problem that one of the tasks can stall the whole pipeline. We call this pipeline stall. And here we have the example of cooking. And I like this example very much. Okay, why? So, for example, we have the pipeline in the fast food restaurant. Okay, and staff is specialized. And one person cuts the bread, another adds the sauces, the third one adds the vegetables, fourth the cheese, and fifth the meat, sixth assembles the hamburger. Okay. And then a guest comes, you know, they say, like let's say it's a very simple restaurant. Okay, they have only one kind of burgers, and everybody who comes in eats burger. Okay, so they have people coming in, and they can actually make burgers. And by the way, this concept is called speculative execution. Okay, you see guy coming through the door and say, hey, let's do another burger. Okay, so you have the pipeline working, hamburgers are going nicely. So like it's McDonald's. Okay, they don't have a lot of varieties. And then that customer comes in and says, oh, I don't like onions. What happens? He is at the cash register, he orders thing between onions, but you have already hamburgers in your pipeline. What happens? Pipeline stall. You cannot give him the burgers that you prepared. There are 5 guys behind him. Yeah, but he doesn't want the hamburger with onions which your workers prepared. So now everything stops, and the new burger has to come all the way, you know, which then does not have the onions. Maybe not all the way, because if we have the vegetables you see here at the third point, you know, then you just need to restart the pipeline there to put one thing through it for the guy who doesn't like onions. And then the pipeline can resume, and then we are looking at the people coming in, making the burgers, and everything goes smoothly. So actually, if you have enough to the workforce, those people coming into the restaurant don't even notice that actually the preparation of hamburger is not instantaneous things. But then another one comes and said, oh, no, I'm vegetarian, I don't want meat, just plain burger without meat, with cheese and everything, but not meat. Again, you have pipeline stall. 5 people have to wait that one gets his burger without meat. So this is pipeline stall. What is important by pipeline stall? It does resolve on its own. You know, it just slows everything down until the pipeline is literally, let's say, unclogged. Okay, unclogged, things that stopped start to working again. So this is pipeline stall. We have also another concept that are far more problematic. Now, when it says pipeline stall problematic, okay, it gets problematic when you have many people who don't like onions, or if you do this, if you have your burger stand with all the pipeline, everything at the vegetarian convention, yeah, because there will be some people, maybe reporters who will eat meat, but people, vegetarians, they won't eat meat. And then you will have constant jiggling left and right. Your pipeline will be constantly in the chaos, and it will work very slowly. What is the solution then? Don't use the pipeline, okay? Because you have just too many things that are interdependent. Now, yes, Jean, it is Very good. So Jean said, okay, simply not adding onions at the onion stage can be also an option, and the pipeline is not stalled because the worker still does something, just passes the burger forward. That is true. But when the people come and order, if the pipeline is working correctly, the moment they order, they get the hamburger. The guy who doesn't want onion actually needs to rake 3 cycles of the pipeline to get his burger, okay? This is the problem. This is the stall. Yeah. So we have perfectly working pipeline and then it stops. It resolves on itself the way, just like you explained. Yeah. The guy who is otherwise adding the onions just does not add onion, just puts it forward. But still, because and longer the pipeline is, this is the problem. And thank you for actually giving me this idea. If you have very long pipeline, the more problem it is for the pipeline stall. Yeah. Because because in each tick of time, things move through the pipeline, yeah? Okay? And if the stall occurs somewhere at the beginning of pipeline, there are many, many ticks that, you can resolve the pipeline, and that one who has customized burger has to wait for a long time, and everybody else has to wait for him. So how does McDonald's solve the pipeline stall problem? So let's go to the funny parts. We are all tired. So how does McDonald's solve pipeline stall problem? Like you don't want, my daughter doesn't want, how is this? Yeah, certain kind of sour vegetables. So what does McDonald's do? Oh, come on. You eat that kind. Yes, exactly. They put your order on hold and serve others. Yeah, so you can do it. Yeah, but if this happens too often, then you have problems. You have disorganization and things like that. Okay. So another example of pipeline stall is a transport, and we know that thing. Okay, we know that thing. Unexpected weather. Just it does not to be long. Because you can think of the operation for a single flight is also a pipeline. Yeah. So you go in, check your luggage goes parallel to you, but you go through the various stages, then you board the plane, and a certain flight is actually moving the kind of the pipeline is in the airport. And then what happens, it's a bad weather, and 1 hour nobody lands, nobody takes off. What happens if that happens in Frankfurt? Do you know? Have you ever seen this? What happens if there is bad weather in Frankfurt? Well, what happens is that, yeah, flight to Ljubljana are delayed. Everything is delayed. Like everything falls apart. Yeah, and it takes a long time till that smooth pipeline starts to work again. So pipeline stalls are hell of a problem, but they eventually resolve by themselves. Okay. Healthcare, unexpected medical condition of the patient can cause a stall during operation. Anesthesiologist says, oh, it's something wrong with this guy, I cannot put him down, or there is irregular heartbeat, and yeah, he just woke up, and then everybody has to lay down their work. You cannot operate on the patient who is he's still conscious. So that would be also pipeline stall, because there are phases in the surgery that need to be done. Unpredictable weather conditions in this, and so on. Now, this is pipeline stall. What is important with pipeline stall? It reduces our efficiency of the parallel work, but it eventually resolves by itself. But there is more scary concept, and that scary concept is deadlock. Okay, deadlock is the problem. It does never solve by itself, and this deadlock is usually illustrated by philosophers at the table. Okay, how does it look like? This is a classic example, and in many books on parallel processing, this thing is illustrated. This is about the only example from the real world they give it to you. Yeah. So you have 5 philosophers at the round table. Why are there philosophers? I don't know. They can either think of it, so let's call them philosophers. And there are forks placed between the philosophers, and for some very strange reason, each philosopher needs 2 forks to be able to eat. Okay? And now, what is the deadlock here? So if they start asynchronously, not the same time. So if 2 of them grab their forks and start to eat, then we have smooth operation. Okay, because they finish their meal, they put away the forks. Okay, they're dirty, but we don't care about this. And then the other 2 philosophers can take the forks and eat, and so on. The deadlock is when those philosophers actually take just 1 spoon, because they take 1 spoon, they want to take the other one, but the other guy already grabbed the other spoon. So we can come to the situation that every philosopher has 1 spoon, he cannot eat because he have only 1 spoon, he waits for the others to eat, but nobody could eat. So at some time, they cannot do anything. They cannot think, they cannot eat, because nothing goes away. And deadlock is the problem because it needs an intervention. The rules as applied until now for parallel processing, like 2 philosophers eating, they do not apply anymore. Somebody needs to intervene and tell to 1 philosopher, sure, you put one of your forks down. Yeah. Oh, sorry, you put your fork down. Because when he puts his fork down, then the other guy can get his other fork, yeah, starts to eat, and then puts the forks down, and the others can't eat. So deadlocks do not resolve by themselves. They need to be resolved by external force. Okay, so for example, we have 2 tractors with the plow and second with the seeder are required to plowing and sowing, but only one guy, those tractors know which needs to be plowed and sown. So the other guys don't nothing wants to follow the other one, but their roles are reversed. So here, this is maybe a complicating example. We can stay with the philosophers. Okay. So, for example, better example is their music festival. There are 2 performers who need each other for do it. Okay, so let's think the festival in Slovenia, where there are often there are collaboration between the rock artists and let's say folk song artists. Okay, so then you have a musical festival. You have the independent stages. One is for the people who want to listen to the rock. The other is for the people who want to listen to let's say, okay, I cannot find the right like music that is like with accordion and so on. Yeah. And you talk everything but right, because there are no people who like to listen to both of them. If they like rock, they don't like the other one. And there is actually example from people from Slovenia, Shank Rock and Natalia Verboten. Yeah, imagine that somebody puts Natalia Verboten on one stage and the other one on the Shank Rock at the other stage, but then Shank Rock actually needs Natalia Verboten to sing with them one of their songs, and then Natalia Verboten needs them to play with her song. They cannot start. Yeah. So somehow the organizer had to start there and said, well, let's change your schedules. Okay. Let's change your schedule a bit, move it a bit so everybody could collaborate. Okay. So this is actual deadlock. It needs external force, divine force, because otherwise they'll just stand at the stage and look at where is the other guy coming to me? No, he can't. He's waiting for you. Yeah. So this is an example of a deadlock in a musical festival. Okay. Okay, not very far here. We will have the break, okay, or we will go. Perhaps we won't need the break, but we will then talk about this thing. We'll solve some things and so on. We have one more concept to show here, and this is critical section. Okay, what is critical section? A critical section is the part of a task. Okay, part of our task. Where only one of the sub tasks can be in, okay? And I won't go any further here. I'll just see nice things. At the airport, the critical section of the task of getting you from the part where you get in to the takeoff is the actual takeoff itself. Why is the takeoff the critical section of the whole task? Because there could not be two airplanes taking off. Do you understand this? Because if there are two airplanes taking off at the same time, boom. Okay, nobody goes anywhere. Terrible accidents, everything is stopped. So in airport, you have actual critical section, which is the takeoff and landing on the other hand. Yeah, so there cannot be two airplanes and the runway at the same times. Not two of them landing, one of them landing, otherwise other one taking off. It simply does not work. Okay, so this is critical section. Other things can go in parallel. Nobody cares if 2 or 3 or 5 boarding counters are boarding place at the same time. But at the time of the takeoff, all the planes have to go wait after another. And this is critical section. This I think is a great example because you can imagine the fiery crash when basically two airplanes start to take off at the same time. Yeah. Now, the critical area in entertainment is artistic performance, or let's say artistic performance on the stage. There cannot be two bands performing different songs at the same stage. So this is like, say, performance itself is a critical section. It's a music festival, people drink, eat, everything. But when there is the band playing, it can be only one band at the stage. Okay. So this is everything I wanted to say for now. And I would suggest, before everybody runs away, that we can go to assignment solving. Okay. So what I would first, my question is, do you want a break now to pee, to drink something like this? And we continue maybe in 5 minutes, 10 minutes or something like this. And then we go to assignment solving, which is other part of our workshop, because this is not purely my lecture, it's you solving task as well, at least some of it. Okay. So what do you say? Can you tell me what do you prefer? Break or no break? Or how long break? 5 minutes, 0 minutes, please. Because of 5 minutes. Okay. So 5 minutes, let's stay everybody online. Okay. I will just mute my phone and we start in 5 minutes exactly. And I'll just show you how the assignments look like. Okay. And then I will show you also how to log in. Okay, and maybe we can do it together. Okay, and then you can continue. Maybe when you finish the work, you can continue with solving so you get the final result. Okay, so 5 minutes. So I have this here. recording. So here we have the assignment, and you need this link, or you can also just let me see. You can also take a picture of this code, but let's say I will also put this link in the chat, okay? And I will now click on this link, okay? So by myself, and something will open. And oh, I have to log out here, okay? Okay, so after I click on this link, I get, and I will show this so you can see me. Yeah, okay. So do you see this, what I'm showing you? So this is Arnes Učilnice. Don't worry, here it's in Slovenian, but inside there are English questions, okay, for those who are from abroad. So here we have the workshop, okay? I will click on the workshop, and then I have to log in. Now, if you are from the University of Ljubljana, then you continue with the login here. Just click. You just click this University of Ljubljana, and it will put you through the login process of university. Or if you're from any other institutions like Arnes, okay, Arnes or University of Maribor, you can choose University of Maribor, and then you will get their login, okay? So I'm from University of Ljubljana, I'll click University of Ljubljana, and I will log in with my usual username, okay? So if you are a PhD student or a student at University of Ljubljana, this should work for you in general. If it does not work for any reason, I'll show a couple of these things, and then we'll solve these things later, okay? So we'll not extend this workshop too much longer. And then we have here a thing called exam, okay? So here we have exam, and I will click on this exam, and okay, says continue with the last things, and this should work. So Janez Križaj, can you confirm that this works? Hopefully. If not, we will solve this later. So here, we will do this together, okay? We'll do this together. And I would like your feedback, if you can, or your solution in the chat, okay? So, are you ready? Let's start. And I really like at least someone to collaborate with me. So we have this concept, an assembly line factory where each worker performs a specific task at specific point in line. If two workers try to do this task at the same spot simultaneously, it could lead to bottlenecks and errors in production, okay? So what is illustrated by here? Critical section, deadlock, Amdahl's law, inherently sequential task, pipeline store, parallelism, data parallelism. We have a lot of concept here, okay? You're not expected to know everything now. Even now, I'm in doubt what is the correct solution, okay? So each worker performs specific task on specific point of line. If two workers try to do that task at the same spot simultaneously, it could lead to bottlenecks and error in production. What would this be? Two people cannot do at the same time. Jean, you have any idea here, you know? Inherently sequential, yeah, but the rest of it it works, okay? In parallel, this is just a specific point where they cannot do. I will go with this describes the critical section, yeah? And let's see if this, how can I get the feedback here? Critical section. And then, I don't have, like, let's say if I end it up, okay, results. Oh, okay, okay. I can see you working on it, but I'm, okay. So I will leave it like this because I can see it in the real time. For me, it's only a preview, obviously. So let's look at the second one, and you can go at your own pace. Which of the learned concept the following situation describes? Multiple workers can simultaneously save different parts of the product, but each product must go to final quality control check. We cannot conduct the proper inspection until the item is finished. Okay? What is this? So we have one point that actually cannot be done until all the points are done. Yeah. So we cannot conduct the product inspection until the item is finished. This could be either inherently sequential task, but more likely we'll say that this is the concept that illustrates Amdahl's law. Okay. So, and you have many questions here. You can go through, yeah, and you can actually fix your answers. And then at the end, I think you can see your result. Okay. So I would say that it's nice for you if you go through here, and if you don't understand the things, you can ask me even later, even tomorrow or something like that, okay, the day after it. But now, for the sake of finishing early, we can do through some more slides and then we finish with that workshop. You probably agree with it, okay? So I won't wait for you, you know, for half an hour, and then we could then you do, sorry, there are about 20 questions, you know, if you sorry, we go here 15, yeah, 19, and then you have the end. Okay, so it's about 20 questions. If you want, you can go through it now if you're fast enough, or you can go through it later when we finish. Okay, Fernando, you cannot enter the exam. Okay, yeah, that's why we are here to check this. So what happens to you, Fernando? I will pause the resume recording. So two mathematical problems we will talk about are optimization and convolution at the level of general understanding, and we will see how they map to parallel processing. So convolution is, again, don't be afraid about this equation. Convolution is basically the following procedure. We have double summation, so double sum running by K and L, and multiplication of this function H and the, let's say, image or some bigger matrix here. So what does this do? This in each step, K times L steps, sorry, not K times, yeah, capital K, capital L steps, it does the multiplication, and then it adds together, summarizes, sums all of these products together. Okay, so the number of multiplication here is quite high, yeah, because we multiply this image on the right with this small image H. Okay, so you see we have one big batch of multiplication. multiplications. And this is one of the components of deep neural networks. And one of the basic components is convolution. And now my question is, can this thing be parallelized? Okay, so look at this formula. Can these things be parallelized? Can we do these things in parallels? And if we would parallelize this, how would we do it? Okay, expecting your answer in a chat. First question is, can you parallelize? And if, how do we parallelize this? How do we split these tasks? What would be the basic task if we have, for example, like 64 processors? Okay, Jean, have any idea? I will try to ask people who respond before. So Jean, and we have, well, Arslan Ali, yeah. There could be wrong answers. I won't say they're not wrong, no wrong answers. They are wrong answers, and you're cordially invited to submit wrong answer as well. So just we can talk about this problem. Okay. Let us think, you know, before we answer this question, do we have here a large amount of equal input data? Yeah, I would say yes, because we have two large arrays, yeah, I and H, that have many elements, yeah, and we do multiplication of them, yeah. So we have the task of multiplication, and then we have a task of addition, okay? So do any of these things could be done in parallel? Now, first thing, if we go from the other side, we actually cannot do the summation until we multiply these things inside, yeah? So this is pretty obvious. The real problem here is a load of multiplications. Can these multiplications be done in parallel? Yeah, data parallelism here is the way to go. One operation, multiplication, done on a ton of data. Okay, so yes, this thing can be parallelized up to some extent. So multiplication could be actually split. So this I or H could be split, and we could perform some multiplication on M processor. Exactly. Jean Reger said, yeah, these are effectively, in programming sense, there are two for loops, two summations, and we could basically split like 64 processors. We could put 64 blocks of multiplication on different processors, okay? And then after this is done, we need to sum everything together. Now, what is the logic in, let's say, computing for a long time? Multiplications are slow and we don't care about summations. So here we can basically split this thing into many parallel multiplication. And this is exactly what GPUs, graphical processing units, NVIDIA, do when we are running deep neural networks. Yeah. And that's why you see, you can make, if you have big problems like this, you can make use of 1,000 cores, okay? If you need to do, let's say, many these calculations, you can run them in parallel, and this is exactly why we need graphical cards, graphical computing units, NVIDIA cards for deep learning, okay? And then we add things together later because this is not a big problem, okay? So this is convolution neural network. works are very, very nicely accelerated by using GPU, graphical processing units. Now we go to the other task. The other task is optimization. Sorry. Other task is optimization, and this other task works like this. So we have two-dimensional function, okay? And we want to find the deepest area in this function here. So we start somewhere, and based on our previous result, we go further and further and further. So we go into the ridge and try to find the lowest point of that function. This is criteria function. This is also used in deep learning. Now the question is, can we parallelize this? And if, how can we parallelize this thing? So again, we started here. We take a look, where is the steepest point, gradients, descent, where is the steepest descent? We move further, we again check the gradient, we move further in direction of gradient, and we move further in direction of gradient, and so on and on and on. This is quite a long process, so it may take some time. And at the end, we arrived at the bottom, at the optimal part of this valley. Can this be sped up using any kind of parallelization? And with what kind of parallelization? So Jean, Peyman, Fernando, any ideas? Again, no wrong answers. Yes, we begin in the random point, yeah. We begin at one random point, yeah. Okay. So, yeah, you're both right. This is actually open discussion now. Well, if we need to do just one optimization, then this is very typically sequential task. We start somewhere, yeah, we move a bit, and then we evaluate the next step, like just the painter who is painting an artistic picture and needs to look at the model again, yeah. And we made another, then we made another move, and we make another move, and we evaluate. So this is very, very sequential thing. But of course, we could do it in a way how Jean said. We could actually go with the method that is called, Jean, do you know it? Monte Carlo, right? So we could just shoot 100 points and run all of them until we get the lowest point. Now the problem is that, Jean, what do you think? We could just take 100 cores and get 100 results. How much faster would we find the accurate optimum? Will be 100 times faster? Not necessarily, yeah. That depends on the shape of this function. Monte Carlo is very rough method. And what Jean said is very good. We didn't agree to anything on the on beforehand, but Monte Carlo is the big canon, let's say big dump canon of optimization. Yeah. So if you don't have any other idea how to solve this optimization task quickly, you could say, forget about the gradient descent. Just we need 100 times the hardware and just like slam it. Okay. 100 times, let's run something 100 times, and then we see it doesn't work, another 100 times, and then when we're 100,000 times, oh, then we get the solution. Now, Monte Carlo is actually the method that you can use here, but the original gradient descent methods is something that won't work. It cannot be parallelized. Yeah. So what Jean did, he said, okay, you know, well, we can use Monte Carlo and it will work, but gradient descent, like Payman, actually slightly, I think, nudged towards it, is sequential method, so it cannot be parallelized. So you see, when you have these two methods, and one is convolution, the other is optimization, you get the core of deep learning methods, which have both of them. Yeah. And that's why, you know, these things become complicated. How much convolutions do you use? How much optimization do you need? And things like that. So the neural network training works like this. This is a greatly simplified idea. Large number of convolutions, you get the result. Based on the result, you do the one optimization step, and then the large number of convolution is calculated again. And yeah, the idea is this could be done as a parallel task. And what is reasonably that we do convolution in parallel, but it turns out that running Monte Carlo on it would be very inefficient. But yes, if somebody gives you the sole access to the big supercomputer, yeah, like the holidays, nobody's working with it, you can do it with these two. Okay, it's just very, very inefficient. So this is now, let's say, the end of our workshop. We will ask you to fill in the survey. Okay, so what do you think about this? It's unconventional and so on. And the reason I cannot give you the link now is because we forgot to translate it into Slovenia as an English language. Okay. And I will fix it now when we finish, and you will get the link to the questionnaire. For those of you who have been here 80% of time or more, you will get those micro credentials. Okay, so the confirmations that you have been here, which you can, I don't know what is the policy of your employer, your lab, your university, or anything. These are the official confirmation that you did this this workshop. And yeah, if you liked it, I will have multiple workshops that following. One is then for PhD students of University of Ljubljana, but I will open it to others as well. Real introduction, but very, very basic introduction into parallel programming. Okay. And then the next one that we have is introduction into parallel use of GPUs, Janez, right?
Yeah, that's right.
For deep learning. Huh? That's right.
Yeah, for the task of deep learning. Yeah.
For the task of deep learning. Okay. So now the discussion will be open. I don't mind if you don't ask anything. I will now actually stop the recording. Okay.